So in this lecture, we are going to talk about forecasting methods. And the first question comes to the mind is, why so many forecasting methods? The simple answer is that no single method works best in all situations. Some data sets have clear trends, while others are noisy or irregular. So forecasting requirements are also differ in terms of their assumptions or their requirements. Sometimes we care about next week, sometimes we care about the following or the next year, and so on. And the key benchmark that we use is the naive forecast, which is simply use the last observed value. And this often performs well, and it serves as a baseline for evaluating more complex and sophisticated techniques or methods. And we are going to categorize the methods into two major broad categories. The first one, we call it, they are going to be model-based methods, and the other one, they're going to be data-driven methods. So the model-based methods, they are assuming statistical or mathematical form of the data. And in this case, what happens, we fit parameters to the data, and then we use the model to predict the future. And we have classic examples like linear regression, logistic regression, and so on. The other type, which is the other big category, which is the data-driven methods. In this case, we do not start with any predefined structures. So we do not do anything. We let the data speak using the algorithms such as smoothing, naive forecasts, or any modern machine learning techniques like neural network or regression trees. The strength of the model-based methods, when you have only short time series, so when you have only short time series, they are very useful. And the assumptions we impose allow us to get meaningful forecasts with limited data. They also excel and works well at capturing global patterns, meaning the relationship that persists across the entire data set. But the trade-off is that the analyst must choose and specify the suitable model. The strength of the data-driven methods is they work well when the structure of the time series changes over time, or when the model assumptions do not work, or they are questionable or something like this. So because they learn, these types of methods, they learn directly from the data. So they're flexible and easier to automate. But the trade-off is that they typically require more data for training. So that's why you have to be careful. Another type of categories, or another, another categorizing technique is, they differ. The model-based and the data-driven methods, they differ in terms of they are capturing global versus local patterns. So global patterns extend across the whole series, like a steady upward trend, and model-based approaches are well suited here, so they work well. However, on the other hand, the local patterns are the short term, and they may shift over the time. For example, sudden shifts in consumer behavior or seasonal variations. In this case, data-driven method adapt and work well there because they are flexible, remember, with a short memory for fast changes or long memory for gradual changes. Also, you have another type of classification we're going to do is, and this is in the lens of what information goes into the forecast. We have three types. Extrapolation methods, they only use the target series history, like the sales, like the ridership, just one series. And examples about this, ARIMA, naive, exponential smoothing, etc. The second type is the econometric models. They bring the economy here, and this is focusing on the causal relationship. So we have correlations, we have causal relationship here, cause and effect. It's like income explains the spending, right? And the third one, which is the external information methods. This external information method use correlated indicators or extra data sources. And these are called heuristic because they are heuristic. We don't know if they have really a causal effect or link or no. It's unclear. That's why we call them external information. And we are going to mention an example about the lipstick here. So the first technique, or the first method, we call it the extrapolation. And as we said, they just rely on the projecting forecast or forward patterns that found on the target series itself only. So it's like naive Bayes. So if the demand yesterday was 200 units, tomorrow forecast is going to be 200 units. Seasonal naive. Let's say for monthly retail sales, this December's forecast is the last December's sales, right? Exponential smoothing. It's like capturing a trend and seasonality by assigning decaying weights to the past values. Or ARIMA models, which capture autoregressive and moving average patterns in a flexible way. What are the advantages? Simple, fast, and require only one series. Limitations, they're ignoring any relationship among other variables. So we don't think about other variables. Econometric models, on the other hand, this is the different part, because the first one, they just think about the series themselves. Now we are linking other variables of interest. So we have explanatory variables in this case, right? It's like consumption is modeled as a function of income. If the income increases, spending increases, and so on. Or in the energy forecasting, electricity demand and the temperature. So hotter days drive air conditioning, let's say. Or in the marketing, sales are modeled from ads, spending, and product pricing, right? All of these models, they assume we have a kind of a cause and effect relationship, right? We have a cause and effects, and we have to fit the parameters carefully because we have assumptions here. We must check the assumptions, and you have to have a statistical experience. The third one, which is external information and indicators. Sometimes, instead of just using the history of the series itself, the forecasters bring in extra information from outside sources. These outside variables may correlate with the series we want to forecast, even if we do not have a direct causal model. And that's why we call them heuristic approach, that we use this extra information because they seem to help, not necessarily because the theory says it should. And an example, as I said, it's like the lipstick index. They found that lipstick sales tended to rise during recessions. When the times were tough, people cut back on expenses, luxuries, but still they still buy the affordable treats like lipsticks. There is no causal economic model here, but it's like a heuristic indicator. Another example here about the forecasting airfares. Suppose we want to predict weekly airfares. Past airfares and past gas prices are valid inputs, but we cannot use the current week gas prices because they are not, or they are unknown at the forecast time. So what can be done is that we forecast the gas prices, then we use them as a prediction for the airfares. But we have to think about this because in practice, gas prices are so volatile and they are unpredictable. So probably if you use this strategy, the uncertainty maybe we are going to get for the forecasting. The bottom line here is what? Is we only use information that would be available at the time of the forecast. Other than this, we are going to get something called data leakage, and I'm going to talk about this later, and we are going to see it. The other part we are going to speak about is manual versus automation forecasting. Many softwares right now, they are just using the automation forecast. Many forecasters, they're just throwing the data and allow the softwares to do the job and just do the forecasting for me. And this is the difference between manual and automation. So we have to understand the difference. The difference is what? Who's making the key decisions? The human or the machine? In manual forecasting, the forecaster plays an active role. He's the one who chooses the model, check the assumptions, fit the parameters, and monitor the forecast. An example, very simple example about this is the build regression model for the GDP growth. Forecasting is done by the economist, who's the one who takes care of this, adjusts the model based on the policy changes. He's the one who checks the assumptions, etc. Or maybe a retailer. Review forecast for a few high-value products. Maybe he's going to override them when the special promotions are given or planned. So manual forecasting works well when the number of series is small and each one matters a lot. However, We use the automated forecasting when the process is complicated. Not the process complicated. Okay, what is the automated? When the process is done by the algorithm, by the machine, okay? So the system or the machine or the software automatically choose the appropriate model, look at the data, choose the appropriate model like exponential, ARIMA, fit it, update it with a new data if you get a new data, and generate forecast without your intervention as an analyst. This works and essential when you have thousands of series, you have thousands of variables, okay? So this is it's not easy to be done manually. And if you do this regularly, so you have thousands of series and you do this regularly, so this has to be done by the machine, automated. It's like a Walmart. They have thousands of products and you would like to forecast the sales for every single product across every store branch of Walmart. Or maybe predicting electricity demand by region and so on. So in this case, we go for the automation. So the difference between these two is the degree of a human oversight and customization. So for the automation forecasting method, we know we have two categories, as we said, data-driven methods and model-based methods. Data-driven methods easier to automate because they learn directly from the data. They adjust as series evolve. The model-based methods harder to automate. Why? Because we have assumptions. We have to check the assumptions every time, right? So we have a regular checking for the validity. That's why they're harder. Examples of the automated forecasting methods is smoothing methods, neural network, and maybe combined forecasts, like averaging different methods. And we are going to talk about this in a second. What are the risks of automated forecasting? One of the risks is overfitting. Overfitting happens when the model chases the noise instead of chasing the signal. Another challenge is the structure break. This happens, when you have a sudden change in the data generating process. And this actually happened. And we have an example about this, by the way, which is COVID-19. In COVID-19, which is a structural break, right? We have a previously reliable models, but they are now invalid because we had kind of a structural break. Like consumer demand, travel, employment patterns, all of these shifted after COVID. So the data that we used before COVID do not work actually well if you want to do any forecasting about the employment pattern or even offline, online, etc. All of these changes, right? Okay, next, combine forecasts. Here's an example in finance that do not put all of your eggs in one basket. So no single method works best across all situations here in forecasting. How? For example, exponential smoothing may capture short-term seasonality well. However, ARIMA may capture long-term trends. So combining these forecasts can help to strengthen the forecast at the end. And it improves the accuracy and makes the forecast more robust. Another thing is the two-level forecasting. Sometimes we need to conduct two-level forecasting. So we talked about combining forecast. Now we are talking about the two-level forecasting. And why this works? What is the two-level forecasting? Two-level forecasting works because good forecast errors should be random white noise. If they are not, the first model that we use did not capture all of the structure of the data. Example, suppose we forecast monthly sales and we use exponential smoothing. The forecast looks fine, reasonable, but when we plot the errors, we found that, we have a seasonal spike every December. So the first model, that means it did not capture the seasonality. Okay, I'm not going to throw it away, but I'm going to add another model on the errors, like ARIMA. ARIMA model might capture the seasonal structure. So we combine the two, the original forecast plus the predicted errors, and this produced a corrected forecast that is more accurate. And this is useful because different models capture different aspects of the data, right? One might capture the long-term trends, the other one might capture the remaining seasonal cycles or seasonality. Another thing is the ensembles. Ensembles, we do not rely on a single forecasting method, but the way that we do the ensemble is different than the way that we do the two-level forecasting. So here, what we do, we generate forecasts using multiple methods, dozens of methods at once. Then what we do, we average them. So for example, we use exponential smoothing, Riemann, neural network, regression, etc. Then we average their forecasts. Why this is helpful? Because each method has strengths and weaknesses. So one method can be good at capturing trends, the other one is good at capturing seasonal shift. So if the errors are uncorrelated, combining them is going to reduce variance. When to use ensamples? Ensamples are flexible and can be used in multiple situations, like some methods perform better for short horizons, like 1 day ahead. Others, they do well for long horizons, like 6 months ahead. So combining allow to benefit from both short and long-term horizons. Also, weekday versus weekend behavior, because they are different. So some methods, they specialize in each. Also, in multiple data source, measure the same phenomenon. Sometimes we have a multiple data source combined from different sources, like manual versus electronic measures, right? One of the famous examples is the Netflix prize, and we're going to speak about this here. So Netflix prize is a very famous example of the ensemble methods. So there were multiple teams that worked and competed to predict user rating for movies, and the idea to get something accurate more than the Netflix system. And the winning team succeeded not just because they come up with a brand new model, they actually combined dozens of different models. Even models with worse performance individually added value to when they averaged with others. So combining forecasts improved accuracy more than trying to tweak one model forever. Some people, they just try to build one perfect model. They try to tweak it forever, then, it's still working, but it's not as strong as when you do multiple and average them. Because multiple models, again, captures different structures when you average them, so you're capturing different things. The advantage and disadvantage of the ensemble methods: they are more accurate forecasts, lower variance of error, more robust, simple to implement. Disadvantages: they're very intensive in terms of cost, because if you have a huge data and you are building multiple methods, this is going to be expensive computationally, I mean. Also, it requires knowledge of multiple methods and knowledge of the rules, what kind of rules how you are going to average them. This is something has to be standardized. Why they are not common among the forecasters? It's kind of psychological reason. It's like people think averaging weekend forecasts, and some people, they think that, we have to have a sophisticated model over simple just averaging. And some people believe that, just one best model must exist. So this is everything for today.